the optical flow. Okay, anyway, after some process, elect U and V, okay, as the two components of the optical flow, so that UV is a vector, okay, it's a vector. Now, you might wonder how to identify the derivative of the image with respect to x, y, and time t, right? Okay, it's easy, just like the Harris column detection. See here, okay? This is the derivative with respect to x, but it's nothing. It's take the central difference, right? See that? Okay, for point xi, yi, we calculate x plus 1 and x minus 1. So the difference in the x direction. So the derivative with respect to y, again, is nothing but it takes the central difference, y plus 1 and y minus 1. That's it. Okay, it's easy. But for the time, it takes the it can use the current time t and t plus 1, or t and t minus 1. It doesn't matter. Okay, or even you can take t minus 1 and t plus 1. It doesn't matter. But in the original paper, it simply used t and t plus 1. It doesn't matter. Okay, so again, but it don't dare to use one single point to calculate the mean shift of A. It definitely you won't just take the point A. Okay, you won't just take point XA and YA. No. We will take what? Just like Harris column detection, we will calculate the optical flow in the neighborhood, which could be 3 by 3 or 5 by 5. Okay, determine your own application. So, but anyway, you need to identify it in a small window. Okay, not just one single point, because otherwise the optical flow will be very, very noisy. Okay, so that's the idea. It come up here. So it come up with see that we use up to n point. So n could be 9 if we use 3 by 3. Okay. Anyway, for each point, you need to find its neighbor and find the mean. Okay, calculate to construct it as a matrix. Okay. So this is the x-axis, y-axis, the gradient. Okay, based on this calculation, the gradient, we use up to n neighbor point. Okay, and V is the optical flow, U and V. Okay, for one point, and B will be the difference in the time direction. Okay, in the time direction. That's it. So simple. So once you have A, okay, which is the difference in the x-axis, difference in the y-axis, and the difference in the time frame, then we know, well, actually, we should call, A times V. A times V should be equal to B. Okay, should be equal to B. Just based on this equation. Okay, see that? This is A. Just for one point, this is A times B. Okay, should be equal to the derivative, okay, with respect to time. Okay, so we have this equation, A times V equal to B. Okay, and then what we need to solve for is the optical flow, U and V, these two components. So once you have this one, then you solve for the pseudo inverse. Okay, the pseudo inverse, the inverse. It cannot be because inverse must be a square matrix, right? We solve for the pseudo inverse. From pseudo inverse. Okay. And then we can find V. Okay, once you have the pseudo inverse, then times B, then you can solve for V. Okay, which is U component and V component. That's it. And you need to do this for each individual pixel point in the image. Okay, not just for edges. Or you can simply focus on edges, that'll be fine. But usually you need to calculate for every pixel point. Okay. So if this pixel point is a background, then you will return UMV to be 0, right? Because when you shift something, you won't see any changes here, right? Nothing has been changed here. So that's what you got, okay? That's what you got here. So it's simple. And if you want to know, here's how we calculate UMV, let's say. Just a summation of this and that, and that's it, okay? If you want, of course, you can just use OpenCV if you want to use, or you can download the programming code from G-Hop. Okay, there's a lot of different versions. Okay, of optical flow. Lucas is just only one of the example. Very easy to understand. Okay, so that's how we calculate UMV. Okay, and then again, you need to set up a threshold. Okay, to identify as a moving object or a background or nothing still. Okay, or the object, the background, which has no motion at all. Okay, but that's the idea. Okay, so here's an example. Suppose we have this frame T. Okay, the person in the lab move from right to the left. Okay, this is frame T plus 1, and you see this is the corresponding optical flow. Okay, it shows the length of the optical flow for each individual point. So you can see a very short optical flow. It means is the background. Okay, it shows no motion at all. But you can see a lot of motion here. Okay, because the length is quite long, and also if you intensify this optical flow field, you will see it will show different direction. Okay, show direction. Okay, if you run it with OpenCV, you can also print out. Okay, you can print out this optical flow. Here's another example we use here. Okay, this is the image of LCD. Okay. Liquid crystal display on a conveyor. Okay, there's a different time, and this is the result of the optical flow. See that if there's no, it shows for the region that shows no defect, you can see the optical flow is quite small. Okay, the magnitude is quite small, but for the one that shows the Muron defect, the optical flow is quite large. This intensifies some of the background region, okay? And this shows the region around the defect. You can see the optical flow, the length of the optical flow. The same thing here, we structured it into a one-dimensional. See that the value, okay, for the surface without showing any defect, the optical flow, the length is less than 5. But for the defect region, most of the pixel point will show a very high optical flow magnitude. Okay, more than larger than 20. You can see. Okay, that's another application, not just for motion detection, but it can also apply for defect detection, especially in LCD manufacturing. You need to move the large LCD panel on the conveyor, okay? But you fix the camera and the lighting. So when you go through the sensing device, you can see something. Okay, so the defect will move, okay, from one image to next image, and we can use optical flow not just for motion detection, okay, but we can also to use to identify the defect, hardly visible defect. Okay, that's one some of the application. And some, even for the deep learning nowadays, whenever there's a motion analysis, it use this as the input, or it use this as the input, not the original video image. You know what I'm saying? I mean, because you can use optical flow to extract the motion, and then you can identify the behavior or anything could be much better, much easier, instead of you put a series of video frames. Okay, that's another application. Okay, for optical flow, even for the deep learning. Okay, so that's up to you. You want to input the original image in the video, or input the motion representation by optical flow as the input to your deep learning model. That would be another application. Okay, so that's optical flow. Okay, so up to now you have learned a lot. Okay, for thresholding, segmentation, image smoothing, image enhancement, morphology, edge detection, color detection, half transform for line and circle detection, and then some of the basic idea about the motion analysis. Okay, the last part of the traditional the requirement for you, okay, application, and it's a very important topic in the traditional machine vision. Is texture analysis, no matter for defect detection or segmentation. Segmentation not just relied on intensity, color, but it could also depends on texture. Okay, so I will talk about how to extract the texture features in a traditional way. Basically, there's two approaches. One is based on statistical from the spatial domain. The other one is from spectral domain. Okay, 一个是直接从空间域，就是影像；另外一个呢是从它的频率域。When I say spectral domain, I mean Fourier transform. And actually, it should include weather. We don't have a time to talk about weather, okay? But I will say something about Fourier. Okay, if I have a time, I will talk about a Gabor transform, which is a so-called short time Fourier transform. It's very important. In the early day of the deep learning, especially for the feature map, the researchers, they love to compare the feature extracted by the deep learning and compare that with the Gabor filter. You can see some of the similarity. Okay, so I will say something about when we talk about the texture analysis. Okay. Before this should be the last part, and I definitely will finish it by next week. Okay, but before that, let me say something first. Okay, your term project. Okay, your term project. Now, you need to think of what should be your term project. Your term project will include the presentation, okay, and the written report. You will do your presentation in the week of final, okay, of the final exam, okay. No written final exam, okay, but you will do your presentation, and also you need to hand in your written report. So first, starting from today, you have, I give you 2 weeks, okay, to think of, okay, what are you going to do for your term project, okay, and besides your assignment, okay, you might have 2 more assignment. You need to hand in the 3rd one, right? Okay, you will have 2 more, okay. I wish I can give you more so you can practice more, but it is almost a promise, just 2 more, okay, just 2 more assignment. If you can survive it, you can survive it, okay. About the project, two weeks from now, you need to hand in an outline, okay? An outline or call it a proposal. But I just 2 pages outline. Okay. First, specify the title. Okay. I need the title. Okay. Don't just name it machine vision. I need a specific, okay? Make it be specific. And then find your team member, okay? Team member. If you want to do it alone, that'll be fine. But I encourage you to find your team member too, okay? Unless otherwise you have some very specific or necessary reason, you need to 3 in a team, but I don't encourage you to do that, okay? 3 will be 2 max, just 2, okay? And you don't need to do it alone, okay? If everybody just do it alone, then we may not have time to do the oral presentation. I prefer 2, okay? Just find your own team member, okay? Just 2 main team, okay? Then give the title, and then what I need is define what will be the problem that you are working on. I don't need you to tell me what will be the method you are going to use. No, nothing to do with the methodology, but I need to know what will be the problem, okay? What will be the problem or what will be the application, okay? What will be the application? And also what could be the, this may not be necessary, but what will be the data set you are going to use? You are going to use your own data set or what will be the data set? But this may not be necessary, okay? What I need is what will be the problem? What will be the application that you are working on, okay? Just give me 2 pages. I need only 2 pages. You don't need to tell me you are going to use this deep learning, you are going to use Hop transform. No, for the time stage, I don't need the details methodology, okay? I need you to tell me what you are going to do. What I don't approve is don't do face recognition, don't do OCR, don't do fingerprint recognition, okay? Because you can find this application from the public library a lot, okay? I encourage you just focus on application no matter it is for manufacturing application or for service application. Okay. For service application, OCR could be just part of it. Okay, could be just, but I prefer, or just for your to make your daily lives better. That'd be fun. Even it's just for fun. That'd be fun. You know what I'm saying? Okay, just for fun. That'd be fun. That'd be fun. But don't do face recognition. I'm not in, because there are so many tools. Okay, for face recognition, for OCR, for okay. So for manufacturing, for service, industrial, for supermarket, what could be the application, or just for fun? Okay, just for fun. Okay, or for your daily life, that will make your life much more easier. Could be even a very small one. That'd be fun. Okay, you know what I'm saying? Okay. For example, that could be may not be easy for you when you use a Google Map to take you from point A to point B. Sometimes when we come to the crossroad, or there's a bridge, right? You might wonder, should I go up to the bridge or take another route, right? Right beside the bridge. You know what I'm saying? I mean, sometimes you cannot understand what is the map. So, I mean, there are some, such as BMW's a car. They use AR technology. They use the camera to capture the scene, the street, and then they will show you the arrow to make a right turn or left turn or go up to the bridge or something. So that I mean, because you use the camera, what you observe on the screen will exactly the same as you see on the street. You know what I'm saying? 就算像你用 Google Map 的时候，那他跟你讲这个往左，可是呢，你前面看到底这个左是哪一个左，不是吗？可是他已经跟你讲要围靠左，围靠左，那要多围靠左。可是假如说你现在看的就是那个，就是 AR 的技术啊，你直接影像不是吗？你看到影像，那你不会把镜头直接画在上面啊，所以你看到的跟影像是一致的。Okay, if you are interested to do something like this, I mean it's very difficult, but I mean whatever you do, okay. But don't make your term project just another assignment, okay. Don't make it as the last assignment. It's got to be a term project, okay. I mean, should be have the weight to qualify as a term project, but not just assignment. Especially don't repeat what you have done for assignment number 1 or assignment number 2. Okay, so for real manufacturing or service industrial application, or just to improve a little bit of your daily life, that would be fun. That'd be great. Okay. Okay, so turning your online 2 weeks from now. I give it 2 weeks. So, but if you want to talk to me or you want to hang in your online next week, that would be great. Okay, so you need to get my approval to go for your term project. Okay, I want to make sure the task you are working on will meet the requirement of this course. Okay, so that's it. Okay, that's all I ask. Okay, even just for fun, that'd be fun. Just for fun, that'd be fun. Okay, but I encourage you to focus on some application. And for the online, I need only about what will be the problem. that you are going to working on, and what will be the application or applications. Okay, you don't need to mention anything about what will be the methodology you are going to use to solve for the problem. Okay. Okay. So any question? Any question about this or not? In Chinese, let me find if you need to learn. It's clear, right? Okay, good. Then go for it. Okay, then go for it. Okay, you don't have too much time for that, right? I think the semester will be ended by early January. I'm not quite sure. Okay, well, definitely it will be ended by mid-January. Okay, so just work on it. But just don't take just 2 weeks, just like another assignment for your term project. Okay? I need to feel the weight, okay, of this term project. Don't make it another assignment. Okay? That's all I ask. Okay? So this about the term project. Okay? Any question? Okay, if no, still have a little bit of time, let me go back to talk about the textual analysis. Oh, one more thing. Okay, one more thing before we talk about the deep learning. Does any one of you know nothing about the convolutional neural network? I say no nothing means not you know how to use it, you know how it works. Not just I heard of it. No. That's okay. Does anyone know nothing about CNN, or you already have the experience on CNN? Do I have to mention anything about CNN? Now, don't. You're supposed to know nothing about it. That'd be fun, okay? That'd be fun. But if everybody has the experience and they know how to manipulate this model, then I will skip it. I won't say anything because that will take me another week to talk about the detail of CNN. So every one of you have the experience, right? You have code the CNN or use the CNN for some application. Is that true? No. If not nothing, that is okay with me. I just want to make sure. If for you have the experience and good experience, you might thought you know something about it, but actually you know nothing about it. Okay, what I'm trying to ask is, do I need to say something about CNN? Right, prefer, okay? But I don't need to go through all the details, right? Okay, let me ask in Chinese one more time, okay? 这个 convolutional neural network 我假设，假如说你们已经有一些经验了，不可以说只有听过，所以 我只再简单复习一下里面一些重要的概念，这样你同意吧？好不好？比较不会误用。Okay, so if every one of you agree, then I will spend a little bit of time just refresh the CN and remind you what will be the important, especially I mean, I don't need to say much about the convolution, but I need to say something about its detail. And then I will introduce some of the new development of CN-based model. Okay, especially for traditional convolution, and you heard of dilate convolution? Yes, sir. Right. Okay. So I will say something about dilate convolution, and then I will talk about the newly developed CN-based model called convolutional nets, developed by FAIR, Facebook AI research. It claims it's better than transformers. Okay, so I will introduce some of the model based on convolution. I may not have. I think I don't have the time to talk about the transformer. Okay, I don't have the time for the transformer, but personally, I'm quite persuaded with transformer for image application. Okay, but I didn't say transformer is not good enough, but anyway, and also later on after that I will talk about image generation. Okay, GAN definitely it almost the standard, but nowadays you see a lot about the image generation by open AI or stable AI code. You know, you heard something about stable diffusion, right?
Like a diagram tree.
Right. But they basically they still based on CNN. For example, for the stable diffusion, they don't use transformer. And now you know why they don't use transformer, because they are not the best for image generation. So I will take this opportunity to introduce the so-called diffusion, the diffusion model, okay? And also I will introduce a so-called mask autoencoder. A mask autoencoder is developed by He Kai-min. You must know this guy. He Kai-min is a Chinese, but worked in the U.S. Anyway, the very famous residual net is developed by He Kai-min. And also the very famous mask RCN for object detection and object segmentation is also developed by He Kai-min. So I will introduce his newly development. But anyway, I will refresh, okay, here and give you some of the ideas, okay, and also and the so-called dilate convolution, okay. There's a lot of different versions of convolution called dilate. You learn dilation, right? So it means what? It will look a wider range. It's trying to find the association, okay? But without increasing the number of parameters. That's the idea. But you will dilate. Okay, you will dilate the filter. Okay, I will give some of the idea about the convolution. Okay, good. Then next week, besides the texture analysis, just bring the CN material. Okay, I will start it first, then go for the autoencoder. Because for autoencoder, as I mentioned, I will also introduce the diffusion and mask autoencoder. Okay, and then we can go for the generated model. Okay, and that will most part of the deep learning and segmentation. Okay, definitely segmentation, object detection. Okay. Okay. Let's go back to the last part of the traditional machine vision, textual analysis. Okay. In the early day, researchers in this area, they divide into homogeneous texture. Okay, I mean in an image, all the texture are homogeneous. And the homogeneous texture can be further identified as a structural texture and statistical texture. This is the so-called structural texture. Okay, you have the structure. And this is the so-called random texture or statistical texture. Okay. Now, when you from a macro view of the ceiling, look at the cell. Ignore the light. The ceiling is structured texture, right? You can see the grid, right? But you just look at a small piece of the ceiling, it looks like a statistical texture, right? Even for the table, take a look. Okay, this is the statistical texture, okay, because it's distributed randomly, okay. And some other part is not homogeneous. It's so-called non-homogeneous texture. Non-homogeneous texture. Non-homogeneous texture, if you remember when I say something about the in morphology, I give you the example about the multi-crystal silicon wafer. 因为太阳能板有没有？太阳能晶片 you have a lot of different crystal grain, right? Remember what I'm saying? Okay. This so-called non-homogeneous texture. Okay. It's not homogeneous with texture or with random, this so-called primitive. Okay. Will you say this is a texture? No. Right? You know what I'm trying to represent a character or a digit or two. But this is a texture, a statistical texture with the primitive of 2. Okay? Or even this is the structural texture with the primitive of 2. of the carat of 2. Okay, so it depends on how you look for this thing. Okay, you can see this from what? The textile manufacturing, right? You will print something from the clothes. Okay, and everything, if we use the microscope, everything will look like this. Even you think it's uniform. Even for the white word here, say it's uniformly white, but if you magnify the surface, you will see something like this. Okay? So it's very important for surface analysis, okay? Especially for manufacturing, okay? For the material, you need to analyze the material, you to try to find the defect or if the surface is uniform or not, okay? So it's very important. So for the texture analysis, the most important thing, okay, is how to extract the texture features. 你说怎么去攫取这些纹路的特征 ？How to identify the feature? Now maybe you might think of now we have the deep learning model. The good thing about deep learning model is that we human beings don't have to extract the features manually. Instead of we use the neural network to extract the feature for us automatically. And then you use the feature for classification, for segmentation, for detection, for anything. You can combine them all together, okay? But we still need to talk about the traditional way, how to extract it, the texture feature from the spatial domain, which is the original input image, or from the spectral domain. 怎么直接从空间域，就是原始的输入影像，或是呢，如何把原始的输入影像转成它的频率影像。Why we need to transfer the spatial domain into a spectral domain is because it could be much easier to extract meaningful or robust feature from the spectral domain. For example, as I just mentioned, Fourier. You won't be affected by noise. Okay, even the input image is quite noisy, but I will explain why next week. Okay, but anyway, so simply we can identify the texture into a homogeneous texture and non-homogeneous texture, and for the homogeneous texture, you can further identify as a structural texture and statistical texture or random texture. Okay. Even for the texture, it is very difficult to define. But the most of the case, in the traditional way, okay, here are some the texture feature that you can use to identify or to describe the surface. Okay. Of course, the very first one, the easy one, is simply tackle the mean intensity. Okay. The mean or the variance, right? You can calculate the mean and the variance. As I keep saying, the white surface of the wall, the variance could be quite small, but the white ceiling, the variance could be relatively large, right? Compared with the white wall here. So variance could be definitely, if we want to only identify it's a wall or it's a ceiling, then that would be easy just by evaluate the variance. But you know, for a lot of cases, you cannot, for these two cases here, the variance could be the same. The mean could be the same. You cannot identify the difference, okay? So for this one, you might need something else. Okay, you can even measure by their gradient or gradient direction. You can find the direction distribution. For this case here, you can only see a vertical direction, but for this one, you will see some 45 and 100 degree. Okay, you can see the difference here. Okay, or you can measure the coarse or smoothness. Okay, and how to measure it. We'll talk about that later on. Or the direction. Okay, I just mentioned here. You can measure the direction, regularity, correlation, or even the moment. A lot of things. Okay. Here's just some very simple one. I will introduce some more effective, okay, measure in a traditional way. Okay, so as I mentioned here, to extract the feature, you can starting from the spatial domain, which is the original input. Okay, the original image, or you can convert the spatial image into a spectral domain. In the spatial domain, you can measure the statistical features. I just mentioned the mean, the variance, the skewness, okay, the kurtosis. The one I'm going to introduce is the so-called co-occurrence matrix. This is a very famous one before deep learning. Okay, before deep learning. Okay, co-occurrence matrix. The idea of co-occurrence matrix is convert the two-dimensional image into a joint conditional probability function. 联合几率密度函数 and then it try to extract the features from the joint conditional probability. Okay. The other one is transfer the spatial domain into a spectral domain by using the Fourier. And the other one will be Gaussian transform. I will introduce these two next week, okay? And I will focus more on some I will introduce two approach, how to extract the joint conditional probability for structural texture and the statistical texture, and then we can go for Fourier transform, and then we can finish the traditional computer vision or machine vision, and then we can move forward for deep learning. Okay. So working your assignment number 3, you need to turn in assignment number 3 next week, and also talk to your team member. Okay, what you are going to working on for your term project. Okay, so that's so much for today. Any question? Any question? No. Good. Okay, then see you next week.